Uh, Thank you. Hello, everybody. Thank you for having me here. I'm excited to get to escape the Wisconsin winter for a couple days and come join you all out here. So today I'm going to be talking about the project that kind of eats up most of my time these days, which is the SDSS-V Black Hole Mapper program. So to start off, for those of you who don't think about galaxies and supermassive black holes on a daily basis, we care about supermassive black holes because they live at the centers of pretty much all massive galaxies. And galaxies and their supermassive black holes evolve together in some way. Okay, we don't understand exactly what the connection is between supermassive black holes and the galaxies that they live in, but we think that there's a connection there. And so in order to fully understand how galaxies grow and how galaxies evolve, we need to understand their central supermassive black holes. And specifically, we want to know how massive these black holes are, as well as the properties of the host galaxies that they live in order to understand these connections. And so my role in this is to measure the masses, primarily to measure the masses of these supermassive black holes, but also to investigate the inner regions of active galactic nuclei, or quasars. So I'm kind of going to start from an angle of we want to measure black hole masses. Okay, we want to measure black hole masses in as many galaxies across the observable universe as we can. So how do we do this? When we have nearby galaxies where we can resolve the sphere of influence of the black hole or very close to it, okay, we can use the motion of stars and gas that is very close into the black hole to figure out the mass interior and to measure the mass of the supermassive black hole. But thus far, with current technology, we can do this for a few hundred of the most nearby galaxies. But what we want to know is what the black holes are like, what the masses are in galaxies that are much farther away. And we can no longer use these same methods when we're measuring those black hole masses. And so we turn to active galactic nuclei, or quasars, to do this. So here's a little bit of a refresher on AGN structure. Okay, when you have an active galactic nucleus or a quasar, you have a supermassive black hole at the center of a galaxy that is accreting matter rather quickly, particularly compared to quiescent galaxies. You have an accretion disk surrounding that black hole. We have our accretion disk, and kind of in an extended region farther out, we have what's called the broad line region, which is where we get the broad emission lines that are typical in quasar spectra, and I'll show you that in just a minute. We also have numerous other structures. Here we have jets that are commonly observed in the AGN. We have these larger regions such as the narrow line region, which is slower moving gas that is much farther out than the broad line region. And we have this dusty torus, which may or may not actually really look like a donut, but the idea is that this is some kind of obscuring medium that causes us to get a different view of the AGN depending on what angle we're looking at it. So these are kind of the basic parts of an AGN. And when we look at a spectrum of an AGN, particularly in the UV and optical, there's a number of distinct characteristics that we see. So we have our broad emission lines here. Okay, these are coming from the broad line region, aptly named. Underneath the entire quasar spectrum, we have this continuum emission that comes from the quasar accretion disk. Different parts of the quasar accretion disk emit at different lengths, and underneath the entire spectrum, we have what we call the continuum emission. We also see, in some regions of the spectrum, we see narrow emission lines coming from the narrow line region, and less. So today, we're going to be focused pretty much on the broad lines in AGN, because those are what we use to measure black hole masses for the most part. So if we assume that the motion of the gas in that broadline region is by the black hole, we can measure the mass of the supermassive black hole using just a few observable quantities. So in order to measure this black hole mass, we need to know the velocity of the gas, right? We have gas in virial motion around the black hole. We can measure its velocity. If we can measure its distance, okay, or radius from the black hole. And if we can measure kind of the distribution of the gas, then we can measure the black hole mass. So let's talk about how we get each of these quantities when we're looking at AGN. So the most straightforward, in my opinion, is the velocity of the gas, right? Our broad emission lines here are Doppler broadened, which means that broader lines will have faster moving gas. So you can effectively measure the line width, and that gives you an estimate of how fast the gas is moving. Okay, so that's our delta V in our mass equation here. Now things start to get trickier when we move on to the other two quantities we need. So the radius of the broadline region is not as straightforward because in general, okay, now with the exception of some recent experiments using interferometry that have been able to resolve broadline regions, okay, this is just in the past 10 years or so, in some of the nearby AGN, we cannot resolve the broadline region. The broadline region, even AGN, is on the order of micro arc seconds in angular extent. We just don't have the ability to resolve it. So we can't look at an AGN and tell how far away the broadline region gas is from the black hole. So we need another way to get this distance. We need another way to measure the radius of the broadline region. And to do that, we use a technique called reverberation mapping. The basic idea is that quasars and AGN are variable over time. And we see signals that come from the very center of the system, those outward to whatever region you're looking at. This particular image actually shows dust. So this is actually kind of more like the dusty torus region, but the same thing applies to the line region. The signal propagates outwards, and you then see that from farther out. And there's a time delay between when you receive the signal from the central source and when you receive a signal from the broadline region or the torus or whatever you're looking at. So that signal reverberates out. If you can measure that time delay between the two signals, that gives you a light travel time between those two regions, which gives you a distance. So this little inset down here shows a couple of curves of showing continuum emission and the broad H beta emission line emission, just one of our quasars that we've looked at. And you can see that they have similar features, but there is a small time delay between those features. And so reverberation mapping aims to measure that time delay to get an estimate of the between. So reverberation mapping can be done on a number of different scales across an AGN. Okay, if you kind of imagine this is a little cartoon of an AGN, wavelength, or what part of the spectrum you're looking at, you can use reverberation mapping to probe different processes. So for example, you can do X-ray reverberation mapping to probe the very inner edges of the accretion disk and the corona. As we move outward, the disk is hotter and then gets cooler, and so we have optical and UV continuum reverberation mapping that can tell us about the accretion disks. The broadline region explores these larger scales, and dust reverberation mapping can also be done in the infrared as well, and that explores even larger scales. So depending on what wavelength we're looking at, we are actually exploring different structures within the AGN. So for today, my work is pretty much entirely focused on optical and UV reverberation mapping, mostly with the broadline region, but we do some accretion disk continuum reverberation. So I'm going to focus primarily on optical and UV observations for the rest of my talk today. So here's an example of what a real reverberation mapping data set looks like. This is a light curve for a nearby Seyfert galaxy called Markarian 335. The top shows the flux, the continuum flux at 5100 angstroms, and the bottom shows the flux in H beta. And so this particular campaign was 180 days of nightly observation. There's a peak that you can see in both of these light curves, a time delay between those peaks, and that is what we are aiming to measure. So when we look at reverberation mapping data, what we're trying to do is find the best time delay that describes the continuum and the responding light curves as well. And that time delay is then converted to our radius, which we use to measure black hole masses. All right, so that's 2 out of the quantities that we need. The last thing that we need to measure black hole masses is this factor F. And this is where things get even more messy. So F accounts for the geometry, the orientation, and the kinematics of the broadline region. which again, not known off the cuff because we can't image this region in general. Again, with the exception of some recent interferometry, we have no direct imaging of the broadline region. So we don't know what the geometry and orientation is supposed to look like. Over here, I'm showing just a couple of example geometric models of what the broadline region looks like in a few nearby AGN. But in general, we don't know what F is. And so typically, to measure black hole masses, we actually adopt an F factor for the entire AGN population. And that F factor is calculated by and follow the same M sigma relationship as quiescent galaxies. So we have all these galaxies, these quiescent galaxies, where we have dynamically measured masses. We see that they have a nice relationship between the black hole mass and the stellar velocity dispersion of their host bulge. And we say, okay, well, AGN probably follow that same relationship. So let's figure out what F has to be so AGN follow that same relationship. And this is the largest source of uncertainty in black hole mass measurements because we don't expect all AGN to have the same F factor. We also don't know if all galaxies follow the M sigma relationship. We don't know if the M sigma relationship evolves with time. A lot of issues with this. So, but unfortunately, for a long time, it's kind of the best that we've been able to do because we just don't have the information on F. However, within the past, I would say 15 or 20 years, we've been starting to get very high quality reverberation mapping data that allows more insight into the factor F, as well as what the broadline region looks like in individual AGN. So here I'm showing what we refer to as velocity resolved reverberation mapping measurements, where we take, say, the H beta emission line, and we divide it up into profile, and then we measure the time lag between the flux in those bins as a function or compared to the continuum flux. And you can see that there's structure here. So the blue side of the emission line has longer time delays than the red side of the emission line. Okay, and that's actually a signature of inflowing gas. And so just by doing this crude division across the profile of the line, we can now start to gain a little bit of insight into what's actually happening in the broadline region. And if we have really nice data sets, we can fit models to the data and come up with things like this over here, where we actually have geometric models and kinematic models for what the little particles in the broadline region are doing. And we can back out F factors in individual AGN when we really have nice enough data. So thankfully, thus far, we've been able to do this kind of modeling on, I would say, a couple dozen AGN. And thus far, the measurements of F from that modeling have been largely consistent, which is good news. But there's still a lot of work to be done there because we have a couple of dozen objects, but they tend to be local, low luminosity, low reading AGN, just because those are the easiest to observe. And so ideally, we'd like to expand this much farther. So reverberation mapping is a very heavily observationally intensive methodology. These two light curves that I'm showing you here took 180 days of nightly observations. At the time, this telescope was not robotic, so set up observers every night, months. People would go up for a week at a time. We would overlap with the next observer. We played a nice game of observer telephone to teach people how to observe. But it took 180 nights of observing just to get this one measurement that we have. And we were able to get 5 measurements during that season, but it took, again, an entire season plus a couple years of full-time grad student time to extract 5 measurements. And so, in order to get reverberation mapping measurements, we require lots and lots of data. And these data need to have very high signal to noise because we need to be able to disentangle the emission lines from the rest of the spectra. We need to have flux calibrations that are accurate to within a few percent because AGN variability can sometimes be kind of low level, and we need to know that the variability we're seeing actually AGN variability and not just instrument issues, right? Just not calibration variability. You generally also need to observe for a long time. Okay, you need to be able to observe long enough that not only do you catch something interesting happening, but you also are observing long enough that you then catch the response, right? So if you have long time lags, you need to have very long campaigns. And you also need to have a very high time sampling compared to the lag that you're getting. So, if you're only observing once every 2 weeks, you're not really going to be able to detect very well time lags that are like a day. So you need to have high time sampling for a very long time. So these are pretty heavy observational requirements. And so until fairly recently, we were doing reverberation mapping on sort of modest-sized telescopes, one object at a time. And we were very slowly building up a sample, and it took a couple of decades for us to build up a sample of like about 50 AGN where we had measurements. Now, those 50 AGN turned out to be really useful because it turns out once we had 50 or 60 AGN, it became pretty apparent that there was a correlation between the broadline region size that you measure with reverberation mapping and the luminosity of the AGN. Okay, this is actually a pretty tight correlation. This is called the AGN radius luminosity relationship. And the existence of this relationship now meant that we could actually make an estimate of a black hole mass just with a single spectrum. So instead of having to acquire 180 spectra over the course of a season, you could take one spectrum, get a luminosity measurement, get a line width measurement, and that's enough to give you a black hole, albeit at a little bit lower precision than the reverberation masses. Okay, so people have used this relationship, which is calibrated off of reverberation mapping methods, to calculate the masses of black holes across the entire observable universe. So anytime you see a black hole mass claim for like a Z of 8 quasar or something like that, those come from this relationship here. Those come from calculations that are based off of the radius luminosity relationship. Those are based off of reverberation mapping measurements. And so this is a really powerful tool, right? It allows us to make these measurements without having to have such a heavy observational price. But have to be careful with this, and I'll come back to that in a little bit. So when reverberation mapping, the first couple decades of reverberation mapping was basically people just slowly building this sample up. Again, using single slit spectrographs where we could observe maybe up to 10 objects in a single night and get a handful of measurements over a season. And so now reverberation mapping is kind of carried out in 2 different modes. We have single object campaigns, which tend to be really highly detailed campaigns where we target just one or a handful of objects, and we try to hammer at it with all the observational resources that we can get our hands on. The goal is to have really high signal-to-noise light curves, really high signal-to-noise spectra, to get a broad range of multi-wavelength data. So often, especially these days, we've run some HST campaigns where we're observing with HST. That's what this is showing, actually. These are HST light curves. We have UV, and then we also have ground-based optical from the ground, and then we try to get whatever X-rays, infrared we can get to go along with that as well. The problem with these is that they're pretty much limited to fairly local, low luminosity objects because you need to be able to observing time and observe something in when you need a high cadence to observe the local Seifert sample is bright enough for us to do this, again, on kind of like modest-sized telescope. So we don't have the ability to go too far this particular type of campaign, just because typically getting access to the observing resources to do this is difficult. So most of the AGN have been done at a very high level of precision like this, are sort of local low luminosity Seifert galaxies. In the past decade or so, there's also been a move to observe AGN in a different mode. Here, measure black hole masses in a large sample of quasars to expand the parameter space of quasars that we're looking at. So now we're not just focused on local low luminosity Seyferts. We're talking about quasars that are out up to redshifts of like 4 or so. And we're talking about higher luminosities, higher redshifts. We're looking at different emission lines because we're talking about redshifted objects. So we're not just looking at H beta anymore. The goal of these campaigns is very different. We don't have quite the level of detail for these objects. We have good enough data to measure black hole masses, but we don't have good enough data to do velocity resolved reverberation mapping, for example, to learn about the details of the broadline region. So to date, there's been two main survey style, like multi-object reverberation mapping campaigns. One of them is called SDSS. It was run by one of the Australian telescopes and in collaboration with the Dark Energy Survey. And the second is SDSS, which I will come back to. But we've actually had some pretty good success with these so far. And so there's more of these large scale kind of industrial reverberation mapping campaigns coming. The Foremost Tides program is actually scheduled to begin this year. They will be monitoring drilling. So they have several hundred quasars that they'll be looking at as well. And we're also the talking phase programs such as the Mauna Kea Spectroscopic Explorer, which may end up with a reverberation component, or may not. We don't know. So my work, as of the last, I would say, 10 years or so, has focused primarily on the Sloan Digital Sky Survey reverberation mapping efforts. So these first began in 2014 as a part of Sloan 3. And the idea was that they had some extra time in Sloan 3. The Sloan 3 survey was running, and they put out a call for additional programs. And so a couple people, I wasn't involved at this point yet, but people said, yeah, let's take that extra time and do some reverberation mapping. And so they picked a field of 850 quasars, ranging all the way out to redshifts of about 4.5 in a single field. So they could be observed in a single BOSS field. This is a BOSS spectrograph. And there's 1,000 fibers that get plugged into the spectrograph, so you can observe 1,000 objects at once. So 850 of those were pointed at quasars. The rest of them were pointed for calibrations. We also obtained some, in this particular field, which I'll call the SDSS-RM field, was also being targeted by pan-stars and several other photometric surveys as well. So in addition to the spectra that we were going to get from Sloan, there's also a plethora of photometry available as well. So there was actually really good multi-wavelength coverage in general of this field, and so it was a good field to start monitoring. So this program ran from 2014 to 2020. It was a part of both Sloan 3 and 4. And out of these 7-year-long light curves that we produced from of these 850 quasars, we measured more than 300 black hole mass measurements, all of these in quasars at redshifts greater than 0.3. So this plot here is just to show the black hole masses we measured as a function of redshift. The gray points were all of the black hole mass measurements from reverberation mapping before this program started. So you can see most of them were at very low redshift. There was a handful previous to this by doing some very long-term single object monitoring. But we added more than 300 measurements across the range of redshifts. And so this was a huge gain in the diversity of quasars that we now have reverberation mapping measurements for. And we've now expanded out to higher luminosities and higher redshifts by quite a bit. And this was just with the previous program that ended in 2020. Now, the other thing that was affected significantly, and something that I spend a lot of my time thinking about, is the radius-luminosity relationship. Because the relationship, that nice, tight relationship that I showed you before, was calibrated off of the 50 or 60 local Seyfert galaxies. And when we started putting in our SDSS quasars, you can see in red here, the relationship started to look a lot less great. And another team, about the same time, so Do It All in 2019, actually they started pointing this out earlier than that. They started observing a whole bunch of very high accreting quasars. And quasars were starting, their AGN were falling below the relationship too. So now all of a sudden, we were looking at a much larger population of quasars, and the radius luminosity relationship was starting to look really messy. And we were like, oh no, what are we doing wrong? And I was a postdoc when these breadpoints came out, and I spent like weeks just staring at my measurements, wondering what on earth I had done wrong, because none of them fell on the radius luminosity relationship. And I was so stressed out. And we did a whole lot of simulations and a whole lot of other things and determined that this is a real effect. This doesn't look like it's some kind of selection effect. And the fact that another group was seeing this as well in their measurements also made me feel a little better. And so we've determined that there is a systematic offset of tend to be highly accreting AGN from the most well-measured AGN radius luminosity relationship. Now, this is very problematic use of single epoch black hole mass measurements, because all of them, as I said before, rely on this relationship. And so when people are measuring black hole masses in these high redshift quasars or whatever large populations of quasars, they're using this relation. And now we're finding out that not all quasars follow this relationship. And so this has, this has big implications for how precise those mass measurements are. So since we determined that this was a real effect, over the past 5 to 10 years or so, we've been trying to come up with ways to correct for this, ways to that we can do better. And there's been a couple of different methods proposed, such as using iron ratios, which are correlated with accretion, things like that. But thus far, that seems to have worked well in some cases, but not other cases. And so we're still trying to figure out what the best thing to do here is. So something that I've been thinking about, and one of my grad students, Jody Kiyokawa at Madison, has been doing, is we're looking at the UV properties of all the quasars that have reverberation mapping results. And we are looking to see whether there's some kind of correlation between offset on the radius luminosity relationship and the UV optical slope in their spectral energy distributions. So the UV optical slope in a quasar SED depends on the quasar's accretion rate. So if we expect this to be accretion related, we would expect to see a difference in the UV. The UV is actually the light that photoionizes the broadline region, not the optical. So we think that this might be one way forward. Although unfortunately, if this turns out to be the way forward, did I just do that? If it turns out to be the way forward, that means we're going to need to know more information about AGN in order to measure black hole masses. So we've also now been able to better establish radius luminosity relationships for other emission lines. H beta is the most commonly used because it falls in the optical nearby objects, so it's easily accessible. But when you start to move to higher redshifts, we use emission lines like carbon-4 or magnesium-2. And relationships are also still a little bit of a mess. The carbon-4 relationship doesn't look so bad, but we only have one point down here that anchors this whole thing. And so we're working on filling in this relationship so that we get a better handle on whether this relationship even exists or looks the same for other emission lines. Because right now, people are taking the H beta relationship and using it for other emission lines as well. So this program, the 7 years of monitoring of 850 quasars, has produced 34 refereed publications, and we're still going just with that data set. There's so much information and so many different things that we can do with these data. They're not all focused on reverberation mapping. That was the main goal of the program, but a lot of these papers have to do with just variability in general, or host galaxies of these quasars, or broad absorption lines and things like that. So, I think we felt like this program was pretty successful. And so along the way, we decided to go ahead and keep going and go even bigger. And so what I'm working on now is the SDSS-V program, which is called the Black Hole Mapper. So the Black Hole Mapper program itself actually has 3 different components. It has a reverberation mapping component, which is what I'm involved mostly with. It has a component to obtain follow-up spectra of sources. And it has a third component to obtain multi-epoch spectroscopy of a very large sample of quasars, but at a much lower cadence than reverberation mapping needs. So this is to explore the broadband region on dynamical timescales, much longer timescales than reverberation timescales as well. And so those are kind of the 3 prongs of the Black Hole Mapper program. And so what I've been focused mostly on is specifically the reverberation mapping project. So we began observing in 2020 and are now observing 4 reverberation mapping fields. These are smaller fields because the instrumentation has changed. So the BOSS spectrograph in its previous iteration, when we were using plates, had 1,000 fibers. We are now have moved to robotic fiber positioners instead of these giant plates. So now there's little robots that move the fibers around, and we can only get 500 of those. So each of these fields is observing around 400 quasars each. And so we have around 1,600 quasars that we're monitoring total. But instead of just getting, what we got from the first program was actually 90 epochs over 7 years. We're now getting 175 epochs over the end of the program. The program was originally supposed to end in 2025. We have, because of delays due to COVID and other instrumentation type things, and LSST getting delayed, which I'll come back to in just a second. We're going to be observing 2027. But we have been observing some of these fields since fall 2020. And one of them is the SDSS-RM field. So we now have 10 years of data on that one field. The 3 fields have a few years of data as well. So SDSS-V is obtaining a whole lot of spectra. And along with this, we are actually also obtaining a whole lot of photometry. Here's just an example of a photometric light curve that we have, one of our SDSS quasars. This is one of the ones that we've been observing since the first program. So since we have data from pan-stars that go all the way back to 2010, and we have been supplementing our spectroscopy with a variety of sources. So in the north, we've been using some data that we have institutional access to, like the Bach 2.4 meter at Stewart Observatory, or the 3.5 meter WIN telescope, which UW-Madison uses. But we've also been using survey data such as pan-stars and ZTF. So these last years here are primarily ZTF data, which have been really helpful. And in the south, we have our 3 fields that are either southern or equatorial. And we've been observing those since 2019 with the CTIO 4 meter Blanco telescope. And these are all deep drilling fields for the LSST program. So we actually chose those fields because we were hoping for most of our program to overlap with LSST observations. That's been thwarted a little bit. We're hoping we can still get a couple of years of overlap once LSST gets going. But so we have these high cadence photometric light curves as well for our fields. A grad student, Teddy Pena at UW-Madison, who's been handling all the data from the wide variety of sources for the northern field, and Yue Shen at the University of Illinois and his team have been handling the southern fields. So this program not only has a lot of data coming from Sloan, but a lot of data coming from these other photometric programs. So let's talk a little bit about science results that we've been getting. Some of these fields we just have been able to start observing the last year or 2. And there's always a little bit of a delay, right? We have a lot of data, we have a lot of processing, we have a lot of kinks that we need to work out. So the first science results that we have been mostly focused on quasars in the SDSS-RM field, where we've been monitoring since 2014 with SDSS. So for example, here's an example. So one of the quasars in our sample, I'm just going to press play here because it takes a little while. One of the quasars that we've observed, this is a little time lapse that shows the H beta emission line as a function of time. And the blue line shows the median H beta profile, just as kind of like a constant that you can compare it to. And we now have 10 years of data on this quasar. And we notice that things look pretty normal for the most part. But once we start getting into the later years, this broadline region starts displaying some really unusual behavior. We don't usually see the H beta line shift like that. We see it vary. Sometimes the shape varies. Sometimes things wobble around. But we usually don't see the whole line shift like that. And this plot in the middle shows the central velocity as a function of time. And you can see that the emission line changes quite a bit throughout the campaign. And so we saw this and immediately flagged it as something interesting. So there's been a bunch of work going into studies of this particular unusual quasar that we wouldn't have really been able to notice or detect if we didn't have these additional years of data. If we didn't have such a long data set with such a high cadence, we might not have been able to detect this weird behavior. So the first paper came out just kind of showing this interesting behavior. We then followed it up with some reverberation mapping where we got velocity resolved results that show that different emission lines seem to show different kinematic structures in the broadline region. We also see weird changes. So there's sort of, this is just a very strange object, and it makes us wonder how many of our objects are like this, because this one in particular is doing things that we just don't often see. This was then followed up with a study where we did some detailed dynamical modeling, which we actually didn't think was going to be possible with our SDSS spectra. But it turns out that some subset of our quasars, the brightest, essentially, the brightest quasars in our sample, our data are actually good enough for us to fit models to the broadline region. So here's an example of these models. This is just showing the light curve and the average profiles for 3 different emission lines. Over here, these are actually little broadline region geometric models where each little point is a little broadline region cloud. The blue points are moving toward us. The red points are moving away from us. And we see the time lag as a function of velocity at very high resolution. And you can see that magnesium-2 looks a little different than H alpha and H beta, for example. And so these studies did some more detailed looking into, do these broadline regions look different when we are when the object is in a low state? At the beginning of the campaign, the flux is pretty low. Toward the end, the flux gets a bit higher. And we do see that the kinematics of the broadline region appear to change as the flux state of the overall system changes. So those are kind of the preliminary reverberation mapping type results that have been coming from the Sloan 5 data set. One other thing that we've been looking at quite a bit is broad absorption lines in quasars. So the basic idea behind broad absorption lines is that quasar winds can be launched off of the accretion disks, and these winds block light coming from the continuum region, causing absorption features in the spectra. So you can see if you look at this spectrum here, this one has very broad, deep absorption features. And we can actually use the variability in these absorption features to learn about the physical conditions within these outflows. So we have this outflowing gas coming from the accretion disks, and the variability gives us some clues as to what's going on there. And the reason why we care about these outflows is because if these outflows are energetic, they can actually provide significant to the galaxy that the quasar lives in. We think that most of these outflows are pretty close in and they're not doing very much to the host galaxy. But there's been some people arguing that some of the outflows we see are farther out that have significant amounts of energy and could affect the evolution of the galaxies that they live in. So in order for us to resolve those issues, we want to know what's going on here. So the black hole mapper reverberation mapping project actually is a unique opportunity for us to examine these because we have around 90 of them in our original quasar field. We have around 100 more in our additional 3 fields. And nobody has ever had a data set like this where we've looked at a statistically significant sample of bow quasars, both on short and long time scales like this. Usually, when people are studying bow variability, they have a handful of spectra that are usually spread out across a few years. And you can learn a lot from that too, but now we have hundreds of spectra spread over a decade. And so this is a whole new opportunity for us to examine the variability just from with this kind of data set that people haven't really had before. So I have a whole little team at UW-Madison working on various broad absorption line quasars. These are just a couple of examples of a couple of our other targets that we've been looking at. And again, we have on the order of 150 to 200 of these bow quasars in our sample that we are now going to have hundreds of spectra for that are spread over 5 to 10 years. So we've been starting to dive into those data and see what what we can learn. So the first major result that we've had from these investigations has to do with one particular quasar, which I actually looked at back in 2015 when we only had 1 year of Sloan monitoring. So this is what the quasar spectrum looks like. Here's a little zoom in. This is the broad absorption line in question. And these plots over on the right show the strength of the bow, so the equivalent width as a function of time, and the average bow velocity, so the centroid velocity of the bow as a function of time. So this first little chunk of data is what we had in 2015. And we noticed that this quasar's bow was varying a lot on very short timescales. And again, nobody had had data on timescales before. So we wrote it up because we were like, oh, nobody's ever seen bows vary on these timescales before because nobody's had the data. Well, now we decided to, once we had 7 or 8 years of data, we decided to go back and just look at this object. And honestly, I wasn't really expecting to find anything interesting. I just figured it would look variable. Like, so this top plot here doesn't show anything particularly weird. We just see, you know, it got a lot weaker for a while, and then it started to get stronger again at the end. And that's pretty normal variability that we see in broad absorption lines. But when we looked at the average bow velocity, we noticed that there was a very strong trend here. The bow was moving blueward, so higher velocity, so blueward. So it was increasing in its velocity. And something that we actually weren't expecting to see. We've actually done searches for this exact phenomenon before. We're looking for shifts in the velocity of bows before. And there's been around a dozen candidates that people have reported for this kind of acceleration. But usually, again, we only had 2, maybe 3 spectra to look at. And when you only have 2 or 3 spectra, it's very hard to disentangle actual acceleration from like changes in shape of the bow that are due to different processes. And so most of the candidates so far have been like, they're plausible candidates, but we just haven't been sure that we're really seeing like an outflow accelerating. But this time, with 130 epochs over 8 years, we were pretty sure. So we did a little press release, which was kind of fun at AAS, where the headlines got farther and farther removed from reality as the game of telephone was played amongst the reporters. But the idea is just we have this really cool data set that no one's really had before. We were able to really high confidence in a broad absorption line. This plot here shows, it's called a trailed spectrogram, or spectrogram. Oh. Each horizontal line is a different spectrum. It's colored by the strength of the spectrum. So blue shows lower flux, red shows higher flux. So the red here, this is the carbon-4 emission line. This is the carbon-4 bow that we focused on. And you can see time goes down here. So it's kind of like a way of looking at every single spectrum at once. And you can really see on this plot how the broad absorption line starts off shifted over here. And as we go, it shifts off to the to blueward. So this was a pretty clear-cut case because we had so many spectra and because we did all of this. So the interesting thing is that this is also the quasar that we looked at with the 8-year data set. So the fact that the first quasar we looked at showed this signature makes us wonder if maybe this actually is a lot more common and we just haven't ever had the data to detect it very well before. So we're now going through and revisiting all the data that we have in these fields to see if we can find this happening in more objects. Maybe this isn't such a unique thing to happen. And a lot of the models for how BALs are produced do predict that you might see some kind of acceleration. And so it's not necessarily unexpected. It's just that we've never been able to do it before because we haven't had the data for it. So we were kind of excited just because we feel like this data set is already starting to show us that it's really useful to have this really rich spectroscopic data set of thousands of quasars over the next years. So to kind of leave you with that, time variability is a great way to explore supermassive black holes, as well as the inner regions of quasars in general. We've got outflows, we've got broadline regions, we've got dust tori, we've got all sorts of things. And the Black Hole Mapper project, reverberation mapping project, is a very cool data set, and I'm hoping over the next decade or so there will be a lot more coming out in this particular area as well. So you should keep your eyes peeled for more results as we continue to grow this enormous data set. So thank you very much, and I'll take questions. Yeah. Does, yeah. So that's a pretty decent interpretation. So these two are showing strong signs of inflow. This one is showing a little bit of a sign of outflow. But it turns out that if you divide the light curve again into like high and low states, and I can't remember which I would have to dive through to make sure, but like you see stronger inflow in one state and stronger outflow in another state, and then it sort of switches around. So it's not always the same thing. So it really does change on a few year time scales as well.
The second question was about the very high columns, 4,000 solar masses a year, very high flow.
Yeah.
I think I remember in your first paper, 1-day variability, you had straight on the depth.
We do. We have a few. So for context, so this quasar here, what he's referring to is when we wrote this paper in 2015, we took the time scale of variability that we observed in this BAL, and we were able to sort of adopt some model, like assuming the variability is due to change in ionization state of the gas, we can back out a few physical parameters of the system. We do have, so we did a sample study in 2019, Hemler et al. 2019, where we looked at 28 of these quasars. We had 4 years of data at that point. And we found that roughly half of them showed the short timescale variability, similar to the one that we had looked at here. We have not done a detailed dive into all of those. So Zach did, this was a student I was working with at Penn State. We picked a couple of examples of particularly particularly nice variability, I guess, if you will, just, just as demonstrations, and found sort of similar results as we did to mine. But we still have, 20 some to go through in more detail that we haven't looked at in detail yet. So yeah, we haven't explored. Mm-hmm. The relative to. Oh.
You see, you look at a source.
Mm-hmm. So yeah, so the rapid variability, it seems like it does kind of come in spurts, and it doesn't do it all the time. So something like this, I don't think any of the variability down in this region on short time scales is significant. So for a while, it kind of went into this low state where it didn't really do much for a while. And we see that in some of the other ones too, where we would see kind of rapid variability for a couple of months, maybe, I would say like 10 data points or so, and then it would sort of calm back down. Yeah, but it depends on the object. Some of them would only vary once, right? There was like one day where they just blipped, and then we went through to try to make sure that it wasn't some kind of instrumental blip, but other than that, it didn't do very much more. So it seems to be a little bit variable. Yes. So this in particular puts constraints on the models for how BALs are produced. In order to explain the level of acceleration that we view, these models may need to be tweaked, may need to be edited. But it's either, the idea is to provide information for how these BALs are produced, which gives us a little bit more information on like what the likelihood is that they're interacting with the rest of their galaxy or not. Gives us better constraints on where they are when we see them, which is still something that people argue about. So the idea here is kind of to feed these measurements to theorists so that they can better simulate the production of BALs. Yes. Does optical reverberation mapping work well with jets? Do you mean like if we're looking down the jets, or do you mean?
Show those time series where you see the continuum.
Mm-hmm. Yeah.
That emission might not have the same sort of reflection.
Yeah, I think that's right. I mean, so AGN, where we're looking too close to the jet and too much of the continuum contribution is from the jet, that would be problematic for reverberation mapping. Yeah. So most of those, though, the broadline region tends to be washed out a little bit by the contribution from the jet as well. And so those tend to not be great targets for us anyway, because we don't see, we don't see a lot of variability, and the lines are weak compared to the continuum strength. But yeah, that's a good point. Oh, yeah. So the F factor is actually an entirely different problem from the radius luminosity relationship. So the radius luminosity relationship allows us to get R, RBLR, right? Entirely separate from whatever F is. And so any issues with R would be just compounded by issues with F. Yeah, so they're entangled, but they're not, it's a different problem. It means that our radius measurements are more uncertain than we thought they were if we're using that relationship to obtain them. So that combined with our uncertainty on the F factor, just balloons the uncertainties in the actual mass measurements. Yeah. Yes.
I'm trying to figure out what we're actually wearing in the structure of the big rock.
That's a good question. I don't know the answer to that offhand. So this particular program doesn't give us that kind of detail. I'm trying to think about some of the. That's right. Right. So, we do know that the different emission lines arise at different radii in different parts of the broadband region, just because they exist in different conditions. We do think the broadline region is stratified. So again, you see broad emission lines of different species at a wide range of radii. I would say just off the top of my head, I would say we view the broadline region as kind of a continuous flow almost, but it's not necessarily. Yeah. I don't think I have a good answer for that. Yeah, I think it's a little of both, maybe. It's like some kind of clumpy continuous. Yeah, I'm not sure. Yes. Yeah. Yeah, so I guess we haven't, let's see, I would have to think. So most of the work that I'm aware of that has looked into quasar variability in general, it has to do with like the quasar luminosity or the quasar, or the black hole mass. So there have been correlations found between how variable quasars are and their luminosities, and also with black hole mass. Also, the time scale of variability depends on the luminosity. So more luminous quasars vary on smaller amplitudes on short time scales, and longer time scales. It takes them much longer to vary in a specific way. I'm not sure if I'm aware of anything that talks about the host galaxies. So really just the black holes and the quasars themselves, as far as I know. They may be there though, but I'm not aware of them.